Good Friday, or Happy Good Friday. Happy Easter. I'm all dressed up in my Easter hat. I'm ready. We're going to get dressed up this weekend, and we're going to praise the Lord from our Zooms, and we're going to rejoice that we're all still here and we're still healthy. And now we're going to finish what we start talking about our learning objectives that we talked about on Wednesday. We all got through the production of acetyl-CoA. I'm not going to review that. You can review that on the previous lecture. But I just want to remind you that there are 5 steps from when we got pyruvate from the glycolysis cycle, and now under our aerobic conditions, we've converted it to acetyl-CoA. We lost 1 CO2. And now we're going to put it through the citric acid cycle. So in this lecture, we're going to review the 8 steps of the citric acid cycle, and then we're going to briefly go over regulation of the citric acid cycle. So here is the citric acid cycle. It goes in a cycle because we know that we're starting out with acetyl-CoA, and we're in the cycle with a 4-carbon compound called oxaloacetate. Oxaloacetate is produced at the end, and it condenses with acetyl-CoA, either coming from glycolysis or coming from fatty acid metabolism, as we'll see. And then it goes through the cycle ending with oxaloacetate and can keep going through this cycle as many times as we have acetyl-CoA to put into the cycle. The first step would be condensation. We'll go over each step separately, but I just want to point out a few things from this cycle so it won't seem so overwhelming. The first step will be condensation from oxaloacetate, which is the last step in the citric acid cycle, and the acetyl-CoA. So we're going from this 1 2-carbon molecule plus this 1 2 3 4-carbon molecule, and getting a 6-carbon molecule called citrate. So that's where we get the name citric acid cycle, because the first thing is the condensation of acetyl-CoA plus oxaloacetate to get citrate. Eventually, in this cycle, we have 2 carbons are oxidized to CO2. So we see between after step 3 and after step 4, we lose 2 carbons. So that's where those are lost. Here we have 4 citrate. At the end we have 4 as oxaloacetate. So we lose those 2 carbons as CO2. And so that's important because we know that the byproduct of metabolism, when we start out with glucose, we lose carbon dioxide and waters. So glucose plus oxygen that we give in a reaction is going to give us carbon dioxide water. So we see the loss of 2 carbon dioxides here when we metabolize glucose. The 4 carbons left become oxaloacetate again, like I said, ready to accept another acetyl-CoA, and given enough time, 1 molecule of oxaloacetate and the right enzymes can oxidize any number of acetyl groups. Again, these acetyl groups are coming from the glycolysis pathway when we create pyruvate and then turn it into acetyl-CoA, also from the breakdown of fatty acids. We're going to see not too much in terms of energy created, such as ATP, but we're going to see a GTP created this time, and we can think of that as like ATP. 1 GTP molecule gets created. Where our energy is going to come from is the synthesis of this NADH and this FADH2. So these are going to be our electron carriers, where it has a lot of energy potential, and we'll see the fruits of that energy come out in oxidative phosphorylation. So this whole cycle, the purpose of it is to get rid of carbons in the form of CO2, our products of metabolism or catabolism, and the production of these energy carrying molecules, NADH and FADH2, which we see the work in those and getting energy out of glucose and oxidative phosphorylation. Here's just a summary of the sequence of events or reactions that you're going to see in the citric acid cycle. We'll go over all 8 of these reactions in the following slides. But as I said before, we're starting with acetyl-CoA that comes from pyruvate and oxaloacetate, which comes out of the other end of the citric acid cycle to make citrate. So we take a 2-carbon molecule and a 4-carbon molecule and make a 6-carbon molecule. You'll see isomerization reactions just like we saw in glycolysis. We're going to make isocitrate. You will see 2 oxidative decarboxylations where we get rid of 2 carbon dioxides. So now, since we have isocitrate, which is 6 carbons, step 3, we're going to lose a CO2 and get a 5-carbon molecule. Step 4, we're going to lose a CO2 and get a 4-carbon molecule. That's going to be carried throughout the citric acid cycle, ending up as oxaloacetate. We're going to see substrate level phosphorylation, where we have a GTP involved, dehydrogenation. So we're going to utilize the dehydrogenase, FADH2, hydration to make malate, and dehydrogenation to give us NADH. The first step in the citric acid cycle is the condensation of acetyl-CoA and oxaloacetate. And it utilizes the enzyme I'll highlight here, citrate synthase. So that's easy to remember because we're synthesizing citrate, which is a 6-carbon molecule from this 2-carbon molecule of acetyl-CoA, which is derived from pyruvate that comes off of glycolysis, and then the 4-carbon molecule oxaloacetate, which is our end product in the citric acid cycle. So we know we're going to form a carbon-carbon bond, and there's a pretty complex mechanism that goes with this that you don't have to know. But I'm just going to over briefly a couple steps in the mechanism just so you can remember what the product would be from this reaction. Okay, so I'm going to just number the carbons. So we have 1, 2 carbons. These numbers are arbitrary. 2 carbons from acetyl-CoA and then 4 carbons, so I'll name them carbon 3, carbon 4, carbon 5, and carbon 6. So we know we need to get rid of the acetyl-CoA, get rid of the coenzyme A, and then push together the 2 carbons here and the 4 carbons and oxaloacetate to get a 6-carbon compound. All right, so without knowing the entire mechanism, I'm going to show you that somewhere in this mechanism, the amino acids are going to aid in forming an intermediate, so an interlate, intermediate. All right, so ignore the fact that I have 1, 2, 3, 4, 5 bonds around this carbon, and know that at some point we're going to have some amino acid acting as an acid, some acting as a base, and we're going to have an enol intermediate. All right. So when I see this enol intermediate in acetyl-CoA, I say, oh, I have something that can act as a nucleophile. Where's my electrophile? Oh, of course it's here, because my carbonyl carbons are always electrophiles. This one is not a carbonyl, or not a double bond anymore, of course, because we wouldn't have 5 bonds around here. All right, so if I want to utilize this nucleophile, say okay, boom, boom, boom. All right, so now I can push these 2 together. So I have carbon 2 plus carbon 4. All right, so we have carbon 2 joined to carbon 4. So I'll just put a nice long bond here. Oh, that's so ugly. Okay, so a nice bond there. And when we do that, we're going to have to lose this double bond, and we'll add a hydrogen here. All right, so where we get this hydrogen from, some complicated mechanism where we use one of the hydrogens from water. All right, and we know we're going to lose somewhere in this mechanism. It doesn't matter what the mechanism is. Somewhere in this mechanism, we're going to lose the coenzyme A. So we can't have this carbon sitting idly here. We're going to add the OH from water. All right, so now we have gotten rid of the enol because it was just an intermediate. So make sure you take that double bond right there. We've combined carbon 2 with carbon 4 from the oxaloacetate. We lost this double bond, so now we have an OH on carbon 4. We lost the coenzyme A, so we added the OH from water to carbon 1, and then we have citrate here. All right, so yeah, so this is gone. We replaced it with the OH, and at the pH it's deprotonated, but we added the OH from water here. We added a hydrogen here where it was a carbon double bond O, and the oxaloacetate looks the same. So basically we created citrate where our carbons are all here, 1, 2, 3, carbon 4, 5, and 6. They're all condensed together in one compound, and this is essentially an irreversible step in the citric acid cycle, combining a 2-carbon molecule acetyl-CoA plus oxaloacetate to get a 6-carbon molecule citrate, catalyzed by the enzyme citrate synthase. So you do not have to know or memorize the structure of acetyl-CoA and oxaloacetate, and hopefully that was helpful into how do we condense those together to get a 6-carbon molecule called citrate. Step 2 is the isomerization of citrate. So we form a 6-carbon molecule citrate, and now we're going to just rearrange it and make an isomer of it called isocitrate. So what you'll see is not really that much has happened conceptually. You have this OH on carbon number 2. Let me just number the carbons. It's probably good to really keep in mind the carbon's number, whatever numbering system you choose. Keep that numbering system going for each step, because that will help you to know which carbons are leaving, which are staying, at the end. Okay, so we have our 6 carbons. On carbon 3 and carbon 5, we're going to switch the OH and the H. So the only difference between citrate and isocitrate is that on carbon 3 and carbon 5, we flip the OH and the H. Now this reaction is catalyzed by the enzyme aconitase. So usually it's not a whole mechanism, but you should remember the mechanism where we utilize the enzyme aconitase. First, we lose that water, so we lose an OH on carbon 3. We lose a hydrogen on carbon 5, and so we form a double bond there, and this forms cis-aconitate. So you should know this mechanism and this intermediate aconitates. It's just simply we remove the OH and the H in the middle. We remove the water in carbon 3 and carbon 5, and then we shove them back on, but in the opposite order. So the citrate is a tertiary alcohol. It's a poor substrate for oxidation, which is coming up in some subsequent steps. So then we make isocitrate a secondary alcohol because it's a better substrate for oxidation. In the last step, we created isocitrate. So here's isocitrate. It looks a little bit different, but it's still isocitrate. It's a 6-carbon molecule, and I'm going to go ahead and label my carbons. 1, 2, oh, that's a 3. 2, 3. Carbon 4 is exactly the same, COO minus. Carbon 5 and carbon 6. All right, so we had citrate, and then we created isocitrate. Why did we do that? Because we want to make a substrate that was more susceptible to oxidation. So now we're going to do some oxidation. And so how do we oxidize things? What enzymes catalyze those reactions? Dehydrogenases. So in step 3, we're utilizing isocitrate dehydrogenase. All right, so we have a dehydrogenase. We know we're going to need some cofactors. And the cofactor we've been using is the same one that we're going to use now. Okay, so if I know I'm going to do oxidation, I set it up for oxidation. I go back to my freshman chemistry and I remember, okay, oxidation is loss and reduction is gain of electrons. So we're going to lose an electron, this nice one that's highlighted here, in the form of hydride. So we're going to lose an electron. And who are we going to give it to? Our nice cofactor that we've been offering electrons to, our electron carrier, NAD. So we're going to put in an NAD or an NADP. It's just an NAD with a phosphate on it in some organisms. So NAD or NAD plus or NADP plus is going to take that electron, and we're going to get out a nice electron carrier, NADPH. NADPH. So you should remember it's NADPH because most of the time we will be utilizing an NADPH. All right, so we in the first step of the reaction for isocitrate dehydrogenase, we're going to lose a hydride, and that's going to give us an intermediate. The isocitrate dehydrogenase performs an oxidation reaction. So we just said, I'll number these again on this side. We have a 5-carbon molecule, sorry, a 6-carbon molecule, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And we have an oxidation where we're going to remove a hydride from carbon number 5 and donate it here to NADP plus and get NADPH and H plus. All right, so it's not only a dehydrogenase that performs an oxidation, but also it's an oxidative decarboxylation. So we're going to now lose a CO2 as well. The reaction mechanism doesn't really matter because it's just too much going on. So let's forget about the intermediate. We know that when we take out this hydride, we're going to get an intermediate. It's called something. All right, don't worry about it. All right, so we have an intermediate that's formed, and then the next thing that is going to happen at this CO2, carbon number 4, it's going to leave. We have another intermediate, and we're going to have this hydrogen here on the oxygen number 5, or the oxygen of carbon number 5. Replace the CO2. Hopefully this is not completely confusing. Replace the CO2 and we'll put it here. And this is going to form a double bond. So a lot happened there, and a reaction mechanism that you don't need to know. But what you should know is that we have an oxidation, so the hydrogen from carbon number 5 is going to be donated to NADP plus. It's an oxidation. you'll have an intermediate, and eventually we're going to form a double bond for carbon number 5 and oxygen number 5, and we'll have the basically transfer of a hydrogen to carbon number 3 where we lost a CO2. So we should be losing a CO2 and forming a double bond for carbon number 5. And in the end, we're going to get a 5 carbon molecule called alpha ketoglutarate. So we lost the CO2, so now we have less carbons than we had before. We now have a 5 carbon molecule. Carbon, let me write carbon. Five carbon molecule alpha ketoglutarate. So I don't know, this might be confusing, but I'm going to just keep the same numbers. Carbon 1, carbon 2, carbon 3. We lost carbon 4, carbon 5, and carbon 6. But we only have 5 carbons. We lost carbon number 4 as CO2. What you should remember is that there is a oxidation of NAD plus or NADP plus to NADPH, and manganese 2 plus is a cofactor that facilitates the decarboxylation, but you don't have to really know the mechanism or the role of the manganese other than that is involved. So step 4 starts with alpha ketoglutarate. So let me just go in and label the carbons. Carbon 1 from citrate, carbon 2 from citrate, carbon 3, we lost carbon 4 from citrate, carbon 5, and carbon 6. So this is a 5 carbon alpha ketoglutarate. And the enzyme that catalyzes this reaction is called alpha ketoglutarate dehydrogenase complex. All right, so if you have in front of you or you remember, steps 3 and 4 are decarboxylations. So as we have highlighted here, we're going to lose a CO2, carbon 6. But it's also an oxidative phosphorylation. We can tell that by the name of the enzyme, alpha ketoglutarate dehydrogenase. So if we have a dehydrogenase, we're going to be utilizing an oxidoreductase. And we utilize an oxidoreductase, we're doing an oxidation or reduction, but in this case, it's an oxidative decarboxylation. And so therefore, we need a cofactor that's going to be accepting the hydrogen. So what electron acceptor have we been using all along? NAD+. So we're putting in an NAD+. In this case, it's going to accept a hydrogen, and we get NADH. NADH as one of our products. So we saw that before we formed one NADPH, now we're forming one NADH. But also this should bring your mind to, because it's a dehydrogenase complex, it's very similar to PDH, which is pyruvate dehydrogenase complex. So that's how we converted our pyruvate to acetyl-CoA. And so since it's very similar in structure, very similar in mechanism, we're going to have a very similar product. So all of our coenzymes are going to be the same, including coenzyme A. Coenzyme A. So in this alpha ketoglutarate dehydrogenase complex, we're going to add in a coenzyme A, and it's called coenzyme A just to emphasize that the sulfur is going to be attached. So where is it going to attach to without going over at any of the mechanism? This carbon here. So this is going to leave CO2. So out goes CO2. Just breathe it out. There goes the CO2. It leaves. NADH is one of our products. And coenzyme A is going to be attached to the alpha ketoglutarate. And so the end product is going to be a 4-carbon compound called succinyl-CoA, which I'll show you next. Succinyl, I don't want to spell that out, CoA. And also NADH and CO2. All right, so what you should be reminded of, okay, so we're step 4, we start with the 5-carbon alpha ketoglutarate. We utilize an alpha ketoglutarate dehydrogenase complex. So we know it's a dehydrogenase, it's an oxidoreductase, but we also know it's an oxidative decarboxylation because steps 3 and steps 4 both lose a CO2. And since it has a name that's similar to pyruvate dehydrogenase complex, we should know that we are going to be adding in a coenzyme A. So because in this oxidoreductase, we're going to add in our electron carrier, NAD+, and get out NADH. It's an oxidative decarboxylation, so we're going to lose the CO2. And we're going to basically replace that CO2 with coenzyme A. So here we have step 4, utilizing the alpha ketoglutarate dehydrogenase. We started out with the 5-carbon alpha ketoglutarate 1, carbon 2, carbon 3, carbon 5, because we lost carbon 4, carbon 6. It's a dehydrogenase, so we know we're going to add in our cofactor NAD plus and get out NADH. And it's an oxidative decarboxylation, so we're going to lose again carbon 6 as CO2 and basically replaced it with coenzyme A. So we should be reminded that it is similar to the pyruvate dehydrogenase complex. That should help you remember to add in that coenzyme A into the structure. It utilizes the same 5 coenzymes we had before, the TPP, the lipoids, the coenzyme A, the FADH2, the NAD+, and we get an NADH. Everything else is regenerated. Its only differences is the amino acid sequence and substrate specificity, meaning that pyruvate dehydrogenase complex binds more specifically to pyruvate, and the alpha ketoglutarate dehydrogenase complex binds specific to alpha ketoglutarate, but the mechanism would be exactly the same. And then we end up with a 4-carbon succinyl-CoA. So we started out with 5 carbons, we lost the CO2, we basically replaced it with coenzyme A. And so now we have carbon 1, carbon 2, carbon 3. This is carbon 5 because we lost carbon 4, and we also lost carbon 6. So we have 1, 2, 3, 4 carbons succinyl-CoA. So now we're not going to have any more decarboxylations because oxaloacetate, which is the end of the citric acid cycle, only has 4 carbons. So we're going to keep all 4 of these carbons as we go along with the other 4 steps of the citric acid cycle. The next step, or step 5, utilizes the enzyme succinyl-CoA synthetase. So I've shown the whole reaction here just because there's nothing really in the name that's going to help you with this reaction because it's named for the reverse reaction. So we start out with a 4-carbon compound that we had before, succinyl-CoA. carbon 1, carbon 2, carbon 3, we lost carbon 4, and then carbon 5, we lost carbon 6. And then what we can imagine, if we have a coenzyme A, there's no coenzyme A on oxaloacetate. So this is the step that we lose the attached coenzyme A. So that's going to leave. And then we're left with a 4-carbon compound, succinate, which is very similar in structure. Carbon 1 is the same. Carbon 2, CH2 is the same. Carbon 3, CH2 here is the same. And then carbon 5, we lose the coenzyme A, and we get a CO2. So the other oxygen would be coming from the GDP. So it's the first substrate level phosphorylation to give us a GTP. So what we want is energy. So what we get is a GTP instead of a ATP, but it's essentially the same. The mechanism involves including a GDP and an inorganic phosphate and condensing those together to give us a GDP. And the energy from the hydrolysis of the thiester from the from the coenzyme A is used to phosphorylate the GDP. We're almost there. Step 6 utilizes the enzyme succinate dehydrogenase. In the last step, we created succinate, which is 4 carbons. And now we're utilizing the enzyme dehydrogenase, which is an oxidoreductase. And so this time it's not a oxidative decarboxylation. So we're just going to perform an oxidation where we lose not 1 hydride, but 2 hydrides. So the 2 hydrogens that are highlighted here, if we lose 2 of those, we're going to actually form a double bond. So the electron carrier that takes on 2 hydrogens is called FAD. We saw FAD before with the pyruvate dehydrogenase complex. So we're going to put an FAD, and if we add 2 hydrogens to it, we're going to create FADH2. So we're utilizing the dehydrogenase, which means we're going to perform oxidation or reduction. In this case, an oxidation. We're going to lose 2 hydrides from the succinate and form a double bond in between carbon 1, 2, carbons 3 and 5, 2 and 3. That's easy. Between carbons 2 and 3, and they're going to both be donated to FAD to give us FADH2. And the next compound, fumarate. So we have a 4-carbon compound. We're keeping up with our 4-carbon compound from now on because we know that oxaloacetate is only 4 carbons. So here's a full reaction of step 6, utilizing the enzyme succinate dehydrogenase. The succinate is oxidized to a double bond, succinate, and passes the electrons to FAD, reducing it to FADH2, creating our fumarate. This enzyme is membrane bound to the inner mitochondrial membrane and participate in oxidative phosphorylation. So we can see this enzyme utilized later. So we go from a 4-carbon molecule succinate to one with a double bond in between carbons 2 and 3 called fumarate. The next step, step 7 in the citric acid cycle, is catalyzed by the enzyme fumarase. So we have fumarase. This reaction happens in 2 steps where we start from our 4-carbon molecule. I'll name those carbon 1 from citrate, carbon 2 from citrate, carbon 3, we lost carbon 4, and carbon 5. And first we're going to add a hydroxyl group to carbon number 3. So this is going to go into carbon number 3 through some mechanism that you don't need to know. And then we have a carbon ion transition state, and we're going to add an H plus to get the molecule malate. So we go from the 4 carbon molecule fumarate to the 4 carbon molecule malate that now has an OH. We can see that here in carbon 3. So carbon 1 is the same. Carbon 2 got that hydrogen. Carbon 3 now has an OH, and then carbon 5, and that gives us malate. In this reaction, fumarate is hydrated to form malate. It's very stereospecific. OH adds to malate, then H plus adds to the carbanion trans to the OH, or H plus adds to fumarate to form a carbocation to which the OH adds trans. In a net effect, we add a whole water. So we have an OH from water and then the H plus from water. And this reaction is fully reversible at cellular conditions. The last step, we already made it to the end. It's catalyzed by the enzyme malate dehydrogenase. So we've gone over this enough times. We are oxidizing our reactions with dehydrogenases, which is an oxido reductase. So if we utilize a dehydrogenase, we are going to add NAD plus as our electron acceptor and get NADH and H plus. The last structure you already learned in the beginning is oxaloacetate. So we're taking this hydrogen from carbon number 2 and creating a carbon double bond O, which gives us oxaloacetate. This reaction is thermodynamically unfavorable, but at cellular conditions, the oxaloacetate concentration are extremely low because it keeps being condensed with acetyl-CoA to make citrate. So that's what drives this reaction in the forward direction, is to maintain the equilibrium of this reaction, because oxaloacetate is constantly being removed. We now just completed one turn of the citric acid cycle. So there are 8 steps in the citric acid cycle. There are 8 enzymes. There are many substrates and many products. And hopefully you'll be able to, before we go into regulation, fill in what the enzymes are for these reactions. We see that we only get 1 GTP, which can be converted into 1 ATP by another outside enzyme. But we get 3 NADHs and 1 FADH2. So we would see those continue on to the oxidative phosphorylation cycle as electron carriers to give us more energy. That completes the second objective, which was to go over the 8 reactions of the citric acid cycle. The net reaction of the citric acid cycle is to take an acetyl-CoA and 3 NAD pluses. We saw that 1 FAD, 1 GDP plus an inorganic phosphate, and 2 water molecules, and we will release 2 molecules of CO2. We know that's the end product of metabolism, 3 NADHs and 1 FADH2 that can be converted to energy in the oxidative phosphorylation. 1 GTP will use 1 CoA and 3 H pluses. 2 carbons of each acetyl group in acetyl-CoA enter the cycle, and 2 carbons are oxidized to CO2. They're not the same carbons from acetyl-CoA, but 2 are oxidized to CO2. Electrons from this process reduce NAD plus and FAD. 1 GTP is formed per cycle. And that relates to energy as ATP through the reversible nucleoside kinase reaction. And intermediates in the cycle are not depleted. You should also know that many citric acid intermediates are required for synthetic reactions as well, meaning the pathway is amphibolic. So we understand catabolism as that breaking down of our carbohydrates into energy, but also we can use some of these intermediates to actually build up some things that we might need, or precursors of things like amino acids. So it's an amphibolic pathway. That means it performs catabolic reaction intermediates as well as anabolic intermediates. So we would see that citrate can be converted into fatty acids and sterols. Another intermediate in the citric acid cycle is alpha ketoglutarate. It's a precursor to many of our amino acids and purines. Succinyl-CoA is a precursor to porphyrins and heme. Oxaloacetate is a precursor to many other amino acids. It can be converted to PEP, which can give us many more amino acids. So if we're in need of amino acids, we can actually break down glucose into things that go into the citric acid cycle and can be converted to the amino acids that make up our enzymes so our body can continue to function properly. Our third learning objective, which I'll go over briefly, is how do we regulate the citric acid cycle. So the citric acid cycle serves two purposes. One, we know, is to oxidize acetyl-CoA for energy. When we need energy, we can take the pyruvate or energy from our carbs and our fats in order to get more energy through the citric acid cycle. But also it's used to generate precursors for synthesis like amino acids. Most intermediates are just playing the role of recycling to keep the cycle going. But we can have modulators that increase the enzymes in the citric acid cycle, or inhibitors that decrease the enzymes, decrease the rate of the enzymes in the citric acid cycle. When our energy supplies are low, we will use modulators. When our energy supplies are high, there are things that inhibit the enzymes of the citric acid cycle. So we can see that there are several steps in the citric acid cycle that are regulated. So first we might want to regulate the conversion of pyruvate to acetyl-CoA. Why might we not want to convert pyruvate to acetyl-CoA and go into the citric acid cycle? Well, of course, we might not want to do that because we have enough ATP. So if we have enough ATP, or we already have enough acetyl-CoA or NADH or fatty acids, all these things that are saying we have enough energy, then we want to inhibit the pyruvate dehydrogenase complex because we don't need acetyl-CoA. But if we see that AMP is high, well, that means that AMP is high, ATP is low, or NAD plus is high, or these other things that we didn't really talk about, then we might want to enhance the rate of reactions to go from pyruvate to acetyl-CoA. Then if we're utilizing the citrate synthase, which is condensing acetyl-CoA and oxaloacetate, well, we might want to inhibit that if we have enough NADH around or ATP around, because that's saying, okay, there's enough energy. But if there's a lot of ADP, meaning we are creating ADP from ATP, then we might want to enhance that process. The next enzyme that's regulated is isocitrate dehydrogenase. So we inhibit that again if there's enough ATP around, but if you have more ADP around, then that means there's less ATP, there's less energy, and so we want to increase the rate of that reaction. And the fourth enzyme that's regulated in the citric acid cycle is alpha ketoglutarate dehydrogenase complex. So you can remember that both of our dehydrogenase complexes are very endergonic reactions, and so they are regulated reactions, and so they need to be inhibited or enhanced to tell the cell that they have enough energy or they need more energy. So if you see something like succinyl-CoA or NADH in abundance, well, we have enough energy, so we want to inhibit. But if there's a lot of calcium, then it tells the cell that we need more energy. More metabolism is going on to keep going through the cycle at a faster rate. All right, that was enough. That's all I have for you. I'll be putting up a review as soon as I can get that done to make make some points more obvious, ask you some questions that might be similar to test type questions. And I hope this cycle was fun. It's a little bit more complicated, I think, than glycolysis because the enzyme names don't help very much. But it's basically just learning when the carbon dioxide is released and when the NADH or FADH2 is created. Those type of things should be very helpful in getting through and memorizing the citric acid cycle. So I hope you're having a wonderful day. I hope you stay healthy. I hope you stay indoors and not go stir crazy. I'll see you next time. Have a good weekend. Bye-bye.